Today I'm going to solve question number 14 of the chapter 4 of the Goldstein classical mechanics. The question is, what is the height to diameter ratio of the right cylinder such that the inertia ellipsoid at the center of the cylinder is a sphere? Before entering to the problem, you need to understand how to calculate inertia about different axes. Now I'm going to explain some physics which involves in this problem. So first of all, we consider a right cylinder. Right cylinder actually has its area of cross section perpendicular to its height. Let me see, it is r be the radius of the cylinder, s be its height, mb its, I'm so sorry, mb is its mass is m, and let me say c is the center of mass, or let me say o be the center of mass. O lies there, o be the origin, and origin lies at the center of mass. And let me draw three axes. This is z axis, this is y axis, and this is x axis. They are mutually perpendicular axes. Now we are going to calculate the moment of inertia. First of all, you can consider like this. It is a cylinder. Consider this is a right cylinder. It has equal radius everywhere, and this area is perpendicular to this side. Now we rotate it like this, in this way. If you rotate in this way, then you can calculate the moment of inertia about the z-axis. Moment of inertia about z-axis is half of mr square, which is half of mr square. Again, you have two options. This is y-axis and this is x-axis. Whichever method you follow, either this way or this way, in both the cases, you will get the equal inertia. So in this case, I'm going to write Ix equal to Iy, means moment of inertia about x-axis is equal to the moment of inertia about the y-axis. This is all about the moment of inertia and about different axes. So here I have given the moment of inertia for this expression. You can just pause the video and look there. And then I'm going to introduce some terms in inertia ellipsoid. We know that inertia ellipsoid has some radius. It may have different radius along different axes at different positions. Ellipsoid actually is a three-dimensional ellipse. You can consider three-dimensional ellipse like this. For example, you have mm, you have this ellipsoid. Well, so if you take along z-axis, let us say this is our z, take along x-axis, this is our x, and along y-axis it is our y. These three are the radius of the inertia ellipsoid along three different axes. But in this particular case, we consider this moment inertia is a sphere, so it has equal radius around all directions. So we consider a special case of Rx equals to Ry equals to Rz, and this origin lies at the center of mass, and it is at the center of the cylinder. So we are going to apply that approach. This radius of inertial ellipsoid is inversely proportional to the moment of inertia. So you can write those proportionality equations for Rx, Ry, and Rz like this. If you divide equation 1 by 2, that proportionality sign gets changed into the equality sign. Since Ry and Rz are equal in this step, you can just follow the simple mathematics. You will get Iz equal to Iy. Then just substitute the Iz and Iy. Here Iz is moment of inertia about z-axis, which is half of mr square. Iy is moment of inertia about the y-axis, which is also equal to the moment of inertia about x-axis, which is 1/4 of mr square plus 1/12 of mh square, where h is the height of the cylinder and m is the mass of cylinder, r is the radius of cylinder. If you follow simple mathematics, easily you can get the required result, that is yards by d ratio, height by diameter ratio, which is root 3 by 2. So this is the way how I proved this problem. So I guess it is the easiest, simplest, and the shortest way which you cannot find anywhere. This is my personal trick to get H by D ratio.